So, statistical inference. Let's start from a few premises which should get us connected with last lesson. We've seen on last lesson that we can assume that the experimental data come as the result of a deterministic cause-effect process, which we describe by using an equation, the deterministic equation. Deterministic means that there is an equal sign. So I use the equation and I get a result, and that's deterministic, cause-effect. However, unfortunately, what we see is not the result of our equation, because we have a stochastic random component which distorts the results we obtain. We call it random noise or experimental error. So, where does this error comes from? It comes from a couple of things. One, random effects of every nature. I make mistake, the object is irregular, all objects are different. And second, which is more important, is sampling error. I have a huge population. I'm taking a small sample, maybe 4, 5, 6 individuals we've seen, but we are not interested in those individuals because we want to give general conclusions. So if we look at those 6 individuals and simply describe those 6 individuals, we are talking about the sample, but that's not interesting for us. It has no sense. I want to come to you and give you general conclusions. My experiment has shown that, but not with that 6 individuals. I want to give conclusions for the whole population. And this is the process called inference. I look at the sample and I try to reach conclusions about the population. This is my task. I have prepared this graph here, which summarizes the process. I have the population here, and the population is composed by individuals which follow a certain deterministic cause-effect model. So they are as they are because there is a natural law behind the process. I take a sample and I look at the sample, but the sample is not as the population, it is different. So, of course, my sample must be representative. This is fundamental. If the sample is not representative, the experiment is invalid. So we cannot even talk about this situation. So we need to be sure that the sample is representative. And if the sample is representative, however, it doesn't look like the population. Because all individuals are different. And I'm not sure that I took individuals, although they are representative, they do not necessarily have the same characteristics of the population. They have not the same average height, for example. They do not have the same average weight, not the same as the population. It would be close to it, but not exactly the same, right? So it's something like distortion, which is described by this epsilon component here, which we have assumed as Gaussian distributed. Such an assumption is not a general assumption. I can make different assumptions, of course, but we stick to this assumption because it is the most common one, at least at the beginning. Then we can make different assumptions, but we will not consider these situations here. So we make a Gaussian assumption relating to this random component here. So we look at something which is not equal to the population. If the population has an expected value of YE here, I do not observe YE, I observe YO. That is YE plus this stochastic component. Is it clear? So, even if I observe YO, which is different from YE, I want to draw conclusions about the population. So I want to draw conclusions about YE, but I have YO in my hands. So how do I pass from YO to YE? This is the task of statistical inference. Right? So this is my first step for today. So yeah, we said this. The inference is when we look at the sample, but we are not interested in the sample. We want to learn the characteristics of the population. So when we go from the characteristics of a sample to the characteristics of the population, we are doing inference. Yeah, I also said this, but we can read it together. The problems, two problems. First one, the characteristics of every representative sample do not necessarily match the characteristics of the population. Look at representative, it is written in red, just to tell you that the sample must always be representative. Otherwise, we don't have an experiment, right? So we are never sure that the sample is representative, but we adopted a correct method. So we can be as sure as possible that the sample is representative. So no certainty again. It's just the method that makes us sure about the representativeness. So every sample is different. First problem. Second problem. If I make an experiment and I take a second representative sample, I obtain different results. So every time I do an experiment, I get a different result. No way about this. If you have also a small experience with experiments, you know this. So we need to take these things under consideration. So we will work with an example today, a very simple and trivial example. What is different from our example now and from the real working practice is that now we pretend to know the truth, which is something we do not usually know. Now you understand better. We have a well that was polluted with a herbicide. A herbicide is a compound which kills plants. And you might wonder why I want to kill plants if I am a plant breeder. I want to kill the weeds. I want to kill the weed plants. So that's my problem. And I use herbicides. And these herbicides go down along the soil profile and reach the well. And they can pollute my well. So I take 3 water samples and analyze them. So I have a well. Let us imagine that we know the concentration, which is 120 milligrams per liter of this herbicide. Well, you might wonder, and if we already know the concentration, why should we do the experiment? Because normally we do not know the concentration. That's why we do the experiment. But in this case, we need to know what is the truth. Otherwise, we lose the reason. So let's assume we know the concentration. Okay, it's 120 milligrams per liter. And we measure such a concentration by using a chemical instrument which gives a standard deviation equal to 12. Right? So when I measure, no instrument is absolutely precise. Every instrument has its own uncertainty. Usually it is smaller than this. I wanted to make it slightly bigger. Otherwise, it's difficult to show you the effects. But in any case, although it is smaller, the uncertainty is always there. Right? So we have 3 water samples from a well with a concentration of 120 milligrams per liter and produced, these concentration values, produced by using an instrument with a standard deviation equal to 12. So it's 10% coefficient of variability, as you see. So what should we expect when we analyze the data, when we make the analysis? What do you expect? That's my question. So we know the truth. What do you expect to see? So Valeria said, I expect that we have 3 values and all 3 values are equal to 120. So you are okay with your answer. You're okay, but if we assume that there is no experimental error. If there is no experimental error, we are sure we take 3 samples and we should observe 120. But there is the experimental error. And thus, what do we observe?
Different results.
So what we observe is something that is different from 120, because there is such random element which is attached to every observation. So we observe 120 plus a value unknown, totally random, that is different for all observations, right? And so this is random, and we can't model it, but we can calculate the probability. So if we are doing a good job, if we are making correct analysis by following a correct protocol, and if we work carefully, if we are careful not to make mistakes, we can suppose that epsilon is very small and related to the instrument, which produces standard deviation of 12. That means that epsilon should be Gaussian distributed. That's the assumption we made, with a mean equal to 0 and a standard deviation equal to 12. So I wrote the expression like this. You see that y observed for each of the I elements is 120 plus epsilon. where epsilon is not to be modeled because it's random. So we use a probability density function to describe epsilon, as we said last time. And we use a Gaussian probability density function with mean equal to 0, because if the error is purely stochastic, with no systematic error, which we should avoid, then the mean should be 0. This is the so-called law of big numbers, right? But the standard deviation is 12, and you see here. Now, I made a small mathematical passage, which is really trivial. So if the error is Gaussian, that means that also the concentration is Gaussian. I simply have to replace 0 with 120. And so I can write that the concentration, the observed concentration for the 3 water samples is Gaussian with mean equal to 120, that is the mean of the well, right? The real unknown concentration, and the standard deviation of 12. So this is the situation, right? The students here, your colleagues are telling me that it's okay because they are doing like this, which means it's okay, I guess. What about home? Is our starting point clear? Because if the starting point is clear, now we're going to do the experiment. Florinda is clear, but do you know which are your colleagues and which are the PhD students? If Florinda is one of your colleagues, okay. No, because I'm very much clear that from home I have only PhD students and none of your colleagues.
I think some of them are giving answers.
Okay, so that's good, but that's different. If they understand and do not give answers because they are shy, it's one thing. The other thing is that they are sleeping or absent or whatever. So you don't know. Okay. What I think is that I had, this is my second online course. Last year I had another group with maybe 15 students, always asking questions, all the moments. And I guess that the English language might be a sort of, further problem. Because if you have to speak Italian, you're not shy. You can speak, you know what you can say, but maybe the English language is another. Okay, let's go ahead. So we do the experiment. Now, I'm taking my RStudio. It's not strictly necessary that you take RStudio as well, because we are doing very simple calculations, but if you want to do them, and if you are ready, just do them. I want to obtain 3 random observations from a Gaussian population where the mean is 120 and the standard deviation is 12. This would be my experiment. This is a Monte Carlo experiment, but which simulates the results of a real experiment. The fact is that now we know that the real hidden mean is 120. And in practice, we don't know this. But now we know it. So we can write an experiment. If I do something like R norm, I want to have 3 observations from a population with mean equal 120 and standard deviation equal to 12. There are 2 ways to do this. One is this, and the other one might be something like 120 plus R norm, 3 observations from a population with mean equal to 0 and standard deviation equal to 12. You see that it's the same. In principle, this is the same. I get 3 random subjects. You see? And they are different. They are different, not because the expression is different. The expression is always the same, but they are different because they are random. There is the random component. Now, I am not sure how much you know about random number generation. I assume that you do not know much because it's not normally a part of your study topics so far. Random number generation might seem a trivial thing. It should be easy to say numbers by random numbers, but it is not. So we need very good algorithms to be able to give random numbers according to some frequency distribution. And all these random number algorithms work starting from a seed. I give a seed to R, or if I don't, it takes a seed somewhere, for example, from the position of the memory chips in the computer, from the motherboard, or whatever, or from the date, or whatever. And from that seed on, the algorithm gives numbers which are reasonably independent following some statistical distribution on the long term. Reasonably, not totally, but reasonably, because it's difficult to give completely independent numbers. Therefore, in order to obtain the same results, me and you, we set the same seed. So we do so, set seed, and we use the same seed. For example, 1, 2, 3, 4. This is a stupid seed, but it's a seed. So once we have set the seed, we, oh gosh, it's really difficult for me to. I like the keyboard, but the keyboard is different from the one I have, and therefore, so I assign. I'm assigning 3 random numbers with mean equal to 120 and standard deviation equal to 12. Be careful, we need to submit first the seed and immediately afterward the function to create random numbers. Then we look at the results and we see these 3 results which should be the same for everybody. These are random numbers, so they shouldn't be the same because they are random, but they are the same because we set the same seed at the beginning. So, this is mimicking our experiment. So my expectation was I make 3 analyses and I should always find 120, a concentration of 120. In reality, I do not find such a concentration. I find 3 different concentration values, which are 105, 123, and 133. So 3 different values. They are around 120, of course. The problem now is, if I ask you, what is the mean of the population? Now, let's put ourselves in the normal conditions. We don't know that it is 120. We only know the sample. What can we say, looking at the sample, about the population? This is our job now, right? What would you do? So we have these 3 results here, which should be the same, because I used the same thing at home. So we have these 3 results. How can we describe the population by looking at these 3 results? What is your idea? What would you do? We are looking for the unknown value for the population, so we calculate the mean of the sample to start with. I mean, we calculate some descriptive stats for the sample. That is what we can do. We have the sample, we describe it. So let's do it. I have done it already, but we do it together. We calculate the mean for the sample. I write M. The mean is M. We have M, that is the mean of the sample, and mu, which is the mean of the population. So we will always use Greek letters for populations and Roman letters for the samples. That's the habit. So, mean Y. And we also calculate the standard deviation, which we call S. And the standard deviation for the population is sigma, the Greek letter sigma, right? So, we use the corresponding letters. Standard deviation. Right. Oops, sorry. Again, with the keyboard. Okay, so let's look at M and S. You see that I'm using a semicolon between the 2 letters. That is the same as going to a new line. So I can write 2 commas and separate them with semicolon. So here we go. So we have a mean for the sample that is 120.6. So it is very close to 120, but it is not equal to 120. This is important. Very close to, but not equal to. And we have a standard deviation which is very close to 12, but not equal to 12. Right? So, now that we have seen the sample, what do we say about the population? So, what is mu and what is sigma? I'm mainly interested in mu, not a little bit less in sigma, not because it's less interesting, but my attention usually is on the expected phenomenon, not on the random part. So I'm looking at the phenomenon, the biology of the phenomenon. So, what do we say about the population? What is our inference? What is mu? what would you say about mu? We don't know anything about epsilon. You see, we have no information. I mean, we have information because we know that the original mean is 120, but here we don't have mean, mu. We have n. So if you want to calculate the epsilon value, you should have mu. But you don't. What can we say then about the mean? We cannot say the exact truth, but we know this. The experiments are only an approximation to the reality. But they are a good approximation. Think about this. Science is just an approximation to reality, but non-science is not even an approximation, it's just fantasy. So, better to have a good approximation than nothing. And what is our best approximation about the reality? It's, almost obvious. What can we do without any other information?
Take them as they are here.
Yeah. So what we can say is that the population has the same characteristics of the sample. That's the best we can say. No other possibilities. So, what do we say? We say so. Yeah, this is the first question. What can we say about the population after having seen the sample? This is the question, and this is the answer. We have no other information, so our best guess is that mu is equal to m, and sigma is equal to s. Is it clear? I mean, we have a sample, we have no other information apart from the sample is representative, so the most likely thing is that the sample has the same characteristics of the population, and therefore we assign to the population the same characteristics that we observed in the sample. Right? Right? This is called point estimation, and it is correct because it's the best we can do. But now in this instance here, we know that we are not right, because mu is not 120.6. It is 120. We know now. We know it now. But normally we don't know this. So what we have to know in practical conditions is that we have only in our hands an approximation to the reality. We don't have the reality in our hands. We have something that is probably similar, right? So this is, we need to be humble as scientists. We don't have the truth. We never had the truth. Second question, are we sure about this? Now we are not sure. We know that we are not right. But in all the other situations, we have to suppose we are not right. We can never suppose that our population looks like the sample, because this is simply almost impossible. So what do? We need to be prudent. What would it happen if we repeat the experiment? This is my question. What would it happen if we repeat the experiment? We would probably get a different result. We can do this now. Let's do a second experiment. We do a second experiment. That's pretty easy. Second experiment. We We should also obtain the same result, but it's not said. We obtain the same result if we have set the seed. We did one simulation, and this is the second one for me. Put the code. So this is another simulation. We see that the subjects are different. Not much different, different. Of course, stochastic element changes every time. And mean and standard deviation are different. And you see, now I have obtained 130, which is pretty lower with respect to the population. So you see that according to the standard deviation, I can also obtain rather different results. We can do this a third time. And it's again different, even smaller, 110. Now, maybe if I do this another time, so far we have always obtained something which is below the mean. Now it's getting higher because it's 121. And if I do this again and again and again, I will obtain the values which sit on a Gaussian distribution. Right? So, what is nice about Monte Carlo simulation is that we can do this even 100,000 of times. Now we will write a piece of script which does such repeated sampling 100,000 of times. And we should obtain 100,000 means. And we should see how they behave. Is it clear? Let's look at the slide. So we repeat the sampling process 100,000 times. 100,000 times. We should do this an infinite number of times, but we cannot do this an infinite number of times because infinite is infinite. So we do this an infinite number of times, but a very high number of times. We could do this 1,000,000 times. It wouldn't take much more than a few seconds on our computer. So if we do this 100,000 times, we get 100,000 concentration means, because we have 100,000 samples composed by 3 individuals. And we try next to describe the population of means. So we have a population of subjects, which is our well, and then we have a population of means, which is the result of repeating the experiment a very high number of times. Let's do this. I'll show you. First of all, we set the seed. Okay, 1, 2, 3, 4. Then we prepare a vector to host the means. And the vector is, let's call it result. It's an empty vector. Oops. Here we go. It's very difficult with this keyboard. You see what I've done here? Oh, sorry. Okay. I'm creating an empty vector. Result assigned. You see, this is just an empty vector. It is just to tell R, prepare this vector, because now I'm going to fill it up with the means. But it's empty so far. Now we need to use a for construct. It is like, oops. For. You see, I have a for open and close round bracket, and then I am opening and closing curly brackets. Okay, so this is the skeleton of what we are doing. For means do this, what is written here inside the brackets here, do this several times. How many times? I write here, I in 1 to 100,000. Right? So, what is happening here? I told her, do this while the index I goes from 1 to 100,000. So there is an index which is updated anytime the process is iterated. So first time the index is 1, then the second time the index is 2, and R is doing the process written inside the curly brackets is doing it 100,000 of times. Right? Is that clear for you? This is your first construct, which is a real programming. It's an iteration cycle. So what should it do? I'm giving myself some space here. I should do this. Get 3 subjects. Oops. Yay. Here we go. You see, I'm asking God to get 3 subjects from a Gaussian population and do this 100,000 times. Of course, we should not lose these subjects. So I'm assigning to Y, as I did before. Then I'm calculating the mean of Y, and assigning this, gosh, it's really impossible, to the vector result. Look, I'm using indexing here. I'll tell you what is happening. You may know that I'm using indentation here to have clear that this is a iteration step. Now try to write this down, then we comment for a while. Be careful to the syntax. I'd like to pass you the code, which might be useful so that you can compare with the code. Now, you there? Okay. How about you, Claudia and Valeria? Now, a swift comment, it's in order. What are we doing here? We told her, please, so we set the seed, we created an empty vector, then we told her, do this process between the curly brackets for 100,000 times. And anytime you do this, please update the index I. Okay, so first time the loop is done, a vector Y is created with 3 individuals taken from a Gaussian population. Then the mean is calculated and it is assigned to the result vector in the first position. Because the first time I is equal to 1, so it is written in the first position. The second time that this is done, 3 other individuals are extracted, the mean is calculated, and it is assigned to the vector result in the second position, and so on. So at the end, we should have a vector result with 100,000 positions, and in each position, there is a mean. So this is like repeating an experiment for 100,000 times. Now let's see how the means behave. So we need to run the script step by step, starting from the seed. Otherwise, we get different results. I mean, with 100,000 repetitions, the difference is not big. But never mind. So it takes a few, maybe 1 second, even less, to repeat such an experiment 100,000 times. It's not like in real life. So now I have 100,000 means. Now I have a distribution of means. But all these means come from subjects which are within the original population. Okay, so I sampled the original populations. So we have just one population and we have 100,000 means. Going back to this. Here we have the code. There are some small differences with this code. I brought something different, slightly different here, because I didn't create an empty vector, but I created a vector with zeros. But that's the same, it doesn't change. And, well, I didn't call the sample Y, but I called it sample, but it's the same again. And then what I did here, I'm removing this because I no longer need. I have this vector result. I explore. You see that I can see just the first 1,000 values. All the other ones are cut because there are too many. But I have 100,000 values in my vector. What is the mean? Mean result. This is it. It's 120. I mean, it is not exactly 120, but that doesn't matter. It would be exactly 120 if we had done an infinite number of simulations. Now the number is finite, so there is always some error that is persisting. But you have to be convinced that if I do this an infinite number of times, I will obtain a population of means whose mean is 120. So the conclusion is that if you want to obtain the exact result for an experiment, you have to do that an infinite number of times, which is not possible. Okay? Right. Then what is the standard deviation? The standard deviation is smaller than 12, much smaller. That is 6.94. Right? So this is an interesting result. So I'm repeating. I guess I'm getting boring because I'm repeating always the same things. I think it is, I think it is useful because we, have to familiarize with concepts which are difficult, intrinsically difficult to me, to my intelligence. I mean, maybe for you are easy, but these are difficult concepts for me. I found them difficult. So I go to the. Okay, so I have done one thing which I do not want to do now. I have discretized this meaning, broken the interval into small pieces and counted the subjects in each interval. You can do this at home if you like, just using this code here. This code is, I'm creating a sequence going from 80 to 160, y from 80 to 160. Let's see what is the minimum for our means. The minimum value is 90, roughly 90, and the maximum value is roughly 150, right? So I wanted to go even a bit further. So I discretized in the interval from 80 to 160. Then I used the function hist to count the subjects in each interval. You see that the width of each interval is 2.5. So I have an interval from 80 to 82.5, and then another interval from 82.5 to 85, and so on, counting the subject and representing this subject. And what comes out is a frequency distribution, and it is this one here. So this is the distribution of means. And you see that I superimposed a Gaussian distribution, and they look totally the same. So what we get from the means is a Gaussian distribution which has the same mean of our original distribution, because we know this now, and a smaller standard deviation. So the question is, the fact is, I start from a population. If I repeat the sampling an infinite number of times, I obtain a Gaussian distribution of means, which has the same mean as the original population and a smaller standard deviation. This is called sampling distribution. And it represents very clearly the replicability of an experiment. It's always like this. When I do an experiment, I fall somewhere within this sampling distribution with the mean. I'm not sure I'm exactly capturing the mean of the population. A few steps ahead. We still have some time. So, first question. Why Gaussian and why the mean of the sampling distribution is equal to the mean of the population? Well, there is an explanation that is related to a very famous theorem. It's maybe the most famous theorem in statistics, which is the central limit theorem. I will just tell you what it says. We will not prove it. It's no point. The sampling distribution of every statistic obtained from random and independent samples is approximately Gaussian. Approximately Gaussian. Indeed, it is not necessarily Gaussian, but it's very close to a Gaussian. In some instances, it's purely Gaussian. In some other instances, it's approximated. But still Gaussian, very similar to a Gaussian. And please consider that we are not doing maths here. So approximations are good for us because we have to solve practical problems. So if I have an approximate solution which is good, So it's better to have an approximate solution than no solution, or to have a very difficult mathematical solution. So I don't mind about spending half of my day to calculate something which I can calculate in 1 second with an approximation, as long as the approximation is good, of course. So it is approximately Gaussian and independently from the probability distribution function of the original population. So we started from a Gaussian population at the beginning, but the starting population might even not be Gaussian. The sampling distribution is still approximately Gaussian. This is a very useful theorem because the whole world of parametric statistics is built upon this theorem. And you need to keep that in mind. And if the statistic in the population is mu, the mean of the sampling distribution is mu. So whatever the population at the beginning, whatever the statistic, if we sample, we obtain something which is distributed according to approximately a Gaussian, and the mean of such Gaussian is equal to the value of the original statistic. So this is very important. And now we will use this. Second question. Now we understood why this is Gaussian. So now we know why this is Gaussian. And we know why it has a mean which is equal to the original mean. But we do not know why the standard deviation is lower. In practice, we can still have an idea that it should be lower. Look at here. Look at the tails. Values farther from the mean. They are very unlikely. Having values farther from the mean for the means, it is even less likely because we have to sample three values very far away from the mean to obtain a mean which is far from the mean. I don't know, it's a bad joke of words, but I think you understand. If I have a subject of 140, so I can take a sample of water which has a very high concentration because my instrument is making a big mistake, but this is very rare. So in the original population, this value is rare. If I want to get a mean of 140, I have to take 3 individuals whose mean is 140. So I have to take 3 very rare individuals from the original population. So the probability of getting a mean of 140 is much lower than the probability of getting 1 individual of 140. So that's why we feel that the standard deviation for the sampling distribution should be smaller than the original standard deviation. But then we can still prove this because there is the so-called the law of propagation of errors. So for independent random variables, the variance of the sum is the sum of variances. So this is a very simple law of statistics. It's not even a theorem. It's just an empirical law. Two things. The variance of the sum is the sum of variances. And the second thing, if I take population, which has a variance equal to sigma, and I take all individuals in this population and multiply them by a constant number, for example, k, I obtain a new population which has variance that is equal to the product k squared, but by the original variance. So I take all individuals, I multiply by k, the new variance is increased in reason of the square of the k value. So this can be easily proved indeed, because if you take three values, for example, let me call it y again. Let's put it 100, 101, and 99. So three stupid values. And calculate the standard deviation. And it is 1, of course. If I want to know the standard, I wanted to calculate the variance, indeed not the standard deviation. It is the same, but we do this with the variance. The variance of y is, of course, 1. And if I want to calculate the variance of 3 by y, so I'm taking the three individuals and multiplying by 3, the new variance is exactly 9. You see, it has increased in reasons of 3 squared, that is 9. So this is an example of the law of propagation of errors. So I can take a population and manipulate it and be able to calculate the resulting mean and standard deviation. It doesn't matter for us at this moment. What matters is that if we take three individuals and calculate the mean of the three individuals, the standard deviation of the mean is lower. We had the feeling already, but if you calculate the mean with the theorem of propagation of errors, it is exactly like that, because in our case, the Gaussian distribution has a standard deviation equal to 12. That means that the variance is 144, which is 12 squared. Okay. So the mean is obtained by summing the two subjects. So if each subject has a variance of 144 and I take three subjects, the variance of the sum is the sum of variances. So I have 144 plus 144 plus 144, which is 3 by 144. Right? Then if I want to calculate the mean, first I sum, and then I divide by 3. But then the new variance is divided by 9. So the variance of the sum is 3 by 144. The variance of the product by 1/3 is 3 by 144 divided by 3 squared. That is 144 divided by 3. So, what do I expect from the mean? If the original population has a variance of 144, the variance of the sampling distribution should be 144 divided by 3. And the standard deviation should be the square root. That is, the square root of 144 is 12, which we already know. So it's 12 divided by the square root of 3, which is exactly 6.93. So what we observed, actually. So let's do some summary. Well, if you agree, that is a lesson which can be done in 2 hours. But if you agree, I would stop quite early so that you can think a little bit about what we said, and tomorrow we finish. So it's not a good idea to eat everything in one chunk, because it takes some time. Here we go. What do we learn from here? The estimate of a mean changes from one sample to the other, according to a Gaussian distribution where the mean is equal to the mean of the population and the standard deviation is smaller and it is equal to the standard deviation of the original population divided by the square root of the number of subjects in a sample. So in this case, it is 12, that is the original, divided by the square root of 3, because we have samples with 3 individuals. The standard deviation of a sampling distribution, it is called with a very famous name, that is the standard error. Right? So this is something you need to remember. So what do we do? How do we use such an information? And I will stop here. I will tell you just this, because then there we are. Then tomorrow we will have to expand just a little bit, but there we are. Our uncertainty about mu, so we know m, which was 120.6. We do not know mu, we actually know it, but normally we don't know it. But what we know is that this mu is close to the observed mean. We do not know how it is. So we are uncertain, and we express such an uncertainty by using the standard error. So we say the standard error is, so we see a mean of 120.62. We calculate the standard error, that is 13.95. Please remember that 13.95, it is the observed standard deviation for our sample. Look, we have a sample here. This was our first sample. And these are the mean and the standard deviation. These are the characteristics of the sample. We use the standard deviation to calculate the standard error. So we take the standard deviation of the sample, we divide by the square root of 3, and calculate the standard error, that is something like 8.05, and we express our guess about the mean of the population by using an interval. So we write it is 120.62 PM 8.05. So we see we are not saying the mean of the population is 120 and 0.62 because we know that it is not like this. We give an interval, and in this interval the real mean is captured. So we are not making a mistake at the moment if we say so. So the mean is 100.20.62 PM 8.05, and we got it. And this is what we do in statistics. We cannot avoid doing this because we are always uncertain. And how do we express our uncertainty? We express it by using the standard error, that is the standard deviation of the sampling distribution. Because we know that if we repeat the experiment, the uncertainty of the means is expressed by using a Gaussian distribution, which has a standard deviation equal to the standard error. So we use that. And that's it. That is what we do. We are uncertain, and we disclose the uncertainty. Of course, say if we have a very small error, we have a standard deviation of 12. If the standard deviation is 1, the standard error is smaller, much smaller. So our uncertainty interval is smaller. And if we have a higher number of replicates, so if we have 6 replicates instead of 3, like this, You see, we divide by the square root of 3. If we divide it by the square root of 6 or by the square root of 9, the standard error would become smaller, and our uncertainty would become smaller. That is called confidence interval, but we will talk about this tomorrow, and we will do some exercises. Right? So that's the whole frame for the statistical inference. Statistical inference makes use of intervals. Intervals are built by using the standard error. What is the standard error? The standard error is the original standard deviation, which we estimate by looking at the sample, divided by the number of replicates. And you see, if we had an infinite number of replicates, because we take the whole population, the standard error is 0, because we divide by infinity. So we have no uncertainty about the standard deviation if we could take whole in that's it. So what I just repeating this, then I close. I take a sample. I calculate the mean for the sample. Then I calculate the standard error by using the information I have, i.e. the standard deviation of the sample, and I express my guess about the population by using an uncertain interval, which is built, we will see tomorrow, as a multiple of the standard deviation of the standard error. In this case, I used just a multiple 1, but then I can increase my uncertainty interval. Right? I think it's enough for now. Any questions? I didn't record. Did I record? Okay. Larissa said clear. How about you, Kang? Is it okay? Okay. That's good. It seems to be okay. Then when you look at it at home, it's obscure again. I know this. It's like this. Everything seems to be clear. Then you read the next row. Everything unclear. You need to be used. It's not you. I mean, it's the statistic which is a problem. I've been studying statistics for 30 years now, and I still find things which I do not understand. And there are things which I studied 10 years ago, and now they go unclear again, and I have to study them again. Good. So, see you tomorrow then. Bye-bye. So let's do these exercises. Let's start from the first one. That is very simple. The chemical analysis was repeated 3 times with the following results. Calculate the mean, deviance, variance, standard deviation, standard error, which is supposed to be singular, and confidence interval. Okay. So, we made a chemical analysis in triplicate, which is usual practice. But we want to know about the whole population of replicates we could have done, but we have not done. Right? So this is just a sample. So what I do, I take these 3 values here and copy them. Then we go to RStudio. and we start a new project. So I close everything, open a new script, and clean everything, because I'm starting a new project now. Okay? So I send it here, and everything is clean. The environment is empty, as you see. It was empty already before. Never mind, we cleaned. And now we build a vector to host the three values. Let's call the vector of y. Remember, maybe at this time, in order to create a vector, we use the function c. So c, open and close the brackets, and I take the values here must be separated by commas. Okay, so we have a new object now in our workspace, and it is a numeric vector hosting the result. So we have sample of size equal 3. So, first task, description of the sample. Okay? Well, it is not really interesting as a sample because it is very small, but still we need to describe it, and we need to describe the location and the spread, as this is a continuous variable, because this is a concentration, therefore it is a continuous variable. So we need to describe the location and spread. Location, as we assume that the concentration might behave as a Gaussian distribution, so we use the mean and the standard deviation. So the mean is m, and it is equal to the mean of y. And the standard deviation is S, that is equal to SD y. So we get the mean, that is 145.3, and the standard deviation, that is 22.19 nanograms per gram. Okay. So this is our result. Now the question is, what is the concentration in a whole population? So we stop looking at the sample. We look to the wider population now, and we wonder, what is the mean of the population? What is the standard deviation of the population? So, what is mu E? What is sigma? Okay, so this is our question. So we might say that the most reasonable thing we can do is to say that mi is equal to m and sigma is equal to S. So this is our point estimate. The most reasonable thing we can do. Okay, because we have no other information. If we are strongly convinced that the experiment was valid, then the most likely thing is that the population and the standard deviation, the population mean and the standard deviation, population standard deviation is equal to what we observed on the sample. But we are uncertain, and we know for sure that this equality here, these equalities do not hold, cannot hold. It is impossible that the population has the same values as the sample. It is really an impossible event. Okay, so this is what we must be convinced to. I see a lot of people in television bringing their results as point estimates. It is easy, but point estimates are always wrong, although they are the most reasonable thing we can do. But they are wrong. So we need to build a confidence interval around these estimates. Confidence interval means an interval of uncertainty which we are very confident that contains the true mean. And we see that in order to build an interval, we need a standard error for the estimate. What is the standard error? It measures the spread of the variability across estimates when we repeat the experiment. So what happens if we repeat the experiment? We do not get the same estimates, we get other estimates, and if we repeat the experiment a lot of times, we get a lot of estimates, and those estimates behave as normal, with a certain mean that corresponds to the mean of the population, and with a certain standard deviation, which we call standard error. And the standard error for the mean is equal to S, the estimate for the population, divided by the square root of the number of values, that is 3. So you see it's smaller than the original standard deviation. And it is as small as the number of replicates becomes higher. Because the higher the number of replicates, the higher the reliability of our estimate. That is the fact. Okay, so the standard error of the mean is 12.8. So this was 22. This is 12. A little bit smaller, because the sample is small. And our uncertainty is rather big. And it is reflected in the standard error. Now we use the standard error to build an interval. So we add to our estimate M, we add and subtract a multiple k of the standard error. So this is our expression. Oh, sorry. So now we need to, what is K? What is this value here? The multiplier. Yesterday we have seen that we can think of using K equal 1. That is a possibility. It is a very simple possibility. Sometimes we use the standard error as a measure of uncertainty. And it's done. So our multiplier would be 1. But we need to know that when the multiplier is 1, we have an interval that is rather small. And therefore, the probability that we don't get the true mean, is very high. So, we are very likely wrong. If we don't use the interval, we are always wrong. If we use an interval equal to the standard error, we are not always wrong, but we are wrong in a high proportion of cases. Yesterday we seen that it's almost 45%. So, a very high probability of being wrong. Yeah, that's exactly. So, K must be higher than 1. We could use K equal 2. So, twice the standard error. We know that this would be okay if the size of the sample would be at least 20. Okay, that would be a good approximation. But in this case here, we have 3 replicates, and therefore using 2 would lead us to an error in roughly 20% of the cases, which is still a high probability of being wrong, and we cannot accept it. So we take instead the 0.975, 97.5% percentile from a student t-distribution, which is QT 0.975 with 2 degrees of freedom, because we have 3 individuals, and therefore 3 equal 2 degrees of freedom. Okay? And then we have our confidence interval, which goes from 90 to 200. So, we don't know about the real population mean, the real concentration, the concentration for the whole sample. We took, for the whole population, we took a small sample, we measured the concentration. That concentration was equal to 145. By looking at this, we conclude that the concentration for the whole population must be with high probability within 90 and 200. So, you see, we look at the sample, we are uncertain about our population, and we clearly express our uncertainty in the form of an interval. Okay? Are we sure we are right? We don't know. We don't know whether we hit the real mean or not. But we are confident that if we do this a lot of times, the probability that we are right is 95%. Okay? So, this is the 95% confidence interval. 95% probability of being right should not be interpreted with reference to our exercise here. Because in this case, we do not know whether we are right or we are wrong. We cannot know it. What we know is that if we follow this method and replicate the experiment, this experiment or in another experiment, we know that we make mistakes in no more than 5% of the cases. This is our aim. You might say, well, it's not that much, but this is the interpretation, the correct interpretation of frequentist confidence interval. So we need to interpret it in relation to the possible replicates of an experiment. Okay, so we don't know whether we hit the mean or not. We will never know it, because the only way we could know it is to repeat the experiment an infinite number of times, and clearly we cannot do that. But this is a prudential attitude. Okay, so this is the confidence interval. And now we'll take the final half an hour to do another exercise, maybe two. First, I would like to take the exercise 5, which is 4 in reality, because there is a mistake. This is slightly different. A sample of 400 insects was sprayed with an insecticide, and 136 individuals survived the treatment. Determine the efficacy of the insecticide in terms of proportion of dead insects, together with 95% confidence limits. Okay, so what do we have different? Here we have 400 individuals, and for each individual we observed whether it was dead or alive. So it's a binary variable. It is not a quantity, it's a quality. It's a binary variable. So we cannot play with means or standard deviations here, because we simply can't. We can only count the subjects who survived the treatment and the subjects who died. It is just a count. So here we have exercise 4. It is written 5th, but it's 4. So we take the proportion P, ratio between 136 and 400. So the proportion of surviving insects was 0.34. This is a statistic. It is not a mean. It's not a standard deviation. It is a statistic relating to a sample. So it is a sample statistic. But we need to think about the biggest picture. So we need to think about the population of insects. There are no just 400 insects in the world. So there are many insects. So we have to think what the proportion of surviving insects would be in the population. So we could say that P, that's for the population, is equal to P. Okay? But we know that the point estimate very likely is wrong. Very likely. Not absolutely wrong, but very likely wrong. In this case, it's not a continuous variable. With a continuous variable, we have an infinite number of values within each small interval. Here, it is a discrete variable. So there is 0.34, but then you don't have all values, because the next values would be, for example, 137 divided by 400. So that would be 34.3425. So there is a jump from 0.34 to 0.3425. There is a jump. And the probability that we hit one of these values is low but existent. Okay, so if we say that the population is 0.35, we might be right. We might be, but it is very unlikely. Okay, so we need to build an interval again, as before. Nothing different. What is it different? It is different how we calculate the standard error. Because in this case, we cannot calculate the standard error as we did before, because we have no values. So, the standard error for a binary, for a proportion is as just wondering whether you can see me at home, because I'm seeing something appear which is not.
Yes, we can see you.
Okay, thank you. Sorry, I sent a message which I couldn't interpret. The standard error for a proportion is calculated as this. P multiplied by 1 minus P, it is variance over proportion. The equation we can use, we can start from, and it's slightly different from what we used to use for the mean. So what we have to learn is that every statistic has a different formula to calculate the standard error. So for the mean, we use the standard deviation divided by the square root of the number of replicates. Here, for a proportion, we use another formula. In this case, it is P multiplied, that would be the variance, thus sigma squared. Is P by 1 minus P. Here we go. That's the variance. And the standard deviation, we know that the standard deviation is the square root of the variance. So, S would be the square root of the variance. That would be the standard deviation. We have no difference, because the standard error for the proportion is the standard deviation divided by the square root of the number of individuals, that is 400. So you see, same thing apart from the beginning, because the variance for a continuous variable is calculated by summing the square of the residuals, the squares of the residuals. We did that first lesson. Okay. Here with the proportion, we simply take the proportion and multiply by 1 minus the proportion. It's different. So, the standard error, this is not the standard error of the mean, this is the standard error for P, for a proportion. And here we have this one. Now, it's easy to calculate the confidence interval. We take the proportion, P, and we add and subtract the multiple standard error. What is this multiple here? We have 400 individuals, and therefore we don't need to bother with the student C distribution. We just take 2 as the multiplier, because we know that this is a good approximation. And here we go. So we have seen that P is equal to 0.34, so we have 34% of surviving insects. But if we talk about the population, we cannot say that the proportion is exactly 34%, sorry. We can say that such a proportion is around, it goes from 29% to 39%. Okay, so, and there is 95% of probability that we really get the true population proportion within this interval. So you see that you can as well use the same method to calculate the confidence interval for a proportion. The only different thing is the way how you calculate the variance. For the rest, always the same. Take the standard error and use a multiple of the standard error to calculate an uncertainty interval. So this is an easy exercise. Okay? Always the same problem. Looking at the sample and taking a decision about the population. So it's always same picture with statistics. We will be dealing with this till the end of the course. Okay? Because this is science. This is method. Okay? So you see, the center again is not the data, but the method. Yeah. Last exercise. And I hope the exercise 4. We are dealing with maize seedlings. You know what a seedling is. It is a seed with a small radical out just after germination. We have measured the length of 30 maize seedlings. Again, missing the plural. I have not done a good job yesterday. I corrected today. Treated with selenium in water solution. So I took these seedlings and treated them with a water solution containing selenium.
Excuse me, Professor. I lost the connection. Can you please explain this exercise from the beginning?
You mean the previous exercise or this new one?
Then the one after the break that we started.
Okay, so the previous one. We had a sample of 400 insects. And we sprayed those insects with an insecticide and counted the number of surviving insects. Right? So we had a sample of 400 and 136 survived. So for this case, we did not observe a continuous variable. This was a binary variable because we looked at each insect and observed whether it was dead or alive. So we did not measure anything. We simply classified each insect in 2 categories, dead or alive. And we counted 137 insects alive, surviving the treatment. Okay? So in this case, the exercise is like this. We calculate a proportion of surviving that was equal to 0.34, so 34% surviving insects. And then we wondered, yes, in the sample there were 34% surviving insects. But what about the big population from which we took these 400 insects? What would be the proportion of surviving insects in the population? First of all, we might simply conclude that the proportion in the population is equal to the proportion in the sample. That would be the most reasonable conclusion, but we know for sure that such a conclusion is likely to be wrong, because it is very unlikely that the population has the same number of surviving insects as the sample, because the sample does not necessarily really reflect the characteristics of the population. It is a sample. Therefore, we need to build a confidence interval around the estimate. So we should not say just 34%. We should say it should be between 30 and 38% or something like this, an uncertainty interval. How do we build such an interval? First of all, we have to calculate a standard error for the proportion. And the way we calculate the standard error for the proportion is different from the way we calculate the standard error for a mean. In this case, for the proportion, we use such an expression. We take the proportion and multiply it first by 1 minus the proportion. And this is the way to obtain the variance of a proportion. So we calculate the variance. We proceed the same way as before. We calculate the variance. We take the square root of the variance and we obtain the standard deviation. We divide the standard deviation for the square root of the number of replicates. In this case, we had 400 replicates. And we get the standard error for the proportion. We use the standard error of the proportion to build an interval by adding and subtracting from the mean a multiple of the standard error. And the multiplier in this case should be 2, simply because we have 400 individuals, so a lot of individuals, and we can use a simple multiplier, because that would be a good approximation. So we conclude that in our sample we have 34% surviving insects, but in the population the percentage of surviving insects should very likely be not exactly 34%, but it should be between 29 and 39% with very high probability. Okay?
Yes, okay. And you said that we have to use 2, p minus 2 or plus 2, why? 2?
P minus 2 by the standard error and P plus 2 by the standard error. So we use the same multiplier, either to add and to subtract.
Thank you.
Thank you.